Welcome to the presentation, Graph Analytics and AI, an efficient way to analyze massive data sets. We will be talking from, two companies, Intel and Katana Graph. They have been collaborating to produce products that help customers analyze massive data sets using graph algorithms, and they run absolutely fantastic on Intel hardware. And we will be talking all about that. So Stephen, the next slide is on the notices. So a summary on this, we will be going over a number of benchmark details and performance information. They have been done with specific configurations in mind, and the references of that and what they are, they will be provided as part of the deck. So if anybody is trying to reproduce any of that, please keep that in mind. Okay, so if you look at these three logos and these three companies, what is common amongst these three companies? So we have Google, Amazon, Facebook, and here at least the answer is provided. So the answer is graphs. So one of the most common elements of large data sets and large amounts of data and a new technology coming in to address them is graphs. So some examples, Google uses the PageRank algorithm to index the web, and that's one of the basic fulcrums of their search capability. Amazon uses graph-based recommendation engines to drive their e-commerce business, one of their fundamental business components. Then we have Facebook uses social graphs to find influencers and friends through its associated algorithms. So this is not only are these three companies going in and doing a lot of innovation in this space, Intel is doing that along with Katana Graph and various other companies, and we will be getting into the details as part of this kind of presentation. So the question comes in, what is graph analytics? So graph analytics is a set of techniques to extract information from connections and between entities. So what exactly does that mean? So if you look at the history of computer science, one of the inflection points was the famous bridges of the Konigsberg problem, or what basically led to what we know as graph theory today. So in the modern world, day-to-day living, you'll find that we use graphs day in, day out, like friend recommendation in social networks, in Facebook for using the neighborhood detection algorithm, or understanding the reliability and resilience of power transportation networks with algorithms like the betweenness centrality or the connected component algorithm. Or if you look at in recent times when kind of AI has taken over, with new advances in deep learning and reinforcement learning, impact of drugs on protein molecules, and the new innovation of medicine, and the disease diagnostics, and the leverage of AI and ML on graph data. That's another kind of new usage. A lot of research going on in that particular space. Or if you are to look at any common man uses these days, whether it's in the mobile devices or in any kind of mapping software, the way to find the most optimum way between 2 points in a map. And for using that, we use the algorithm known as BFS, or breadth first search algorithm. So for all of this, this entails graph analytics, graph-based neural nets and AI, and graph databases. And to talk more about that and what Intel is doing in this particular space across hardware and software, I'll turn it over to Ramesh from Intel.
So my name is Ramesh, and I work at Intel in performance analysis and interested in graphs for the challenges that they pose with respect to the performance. Now, when you look at a large number of these domains that are shown here, what you can see is that a large amount of data is being produced in each of these domains. And it is possible to represent all of these data that is being produced as graphs. So for example, if you see message activity in a computer network between different entities, they can be analyzed to see if there are any security threats or if there is any intrusion inside the network. Now, as the size of these graphs become very large, especially when this data is being generated by machines, it is really hard to fit them in a single machine and then try to do the analysis on those graphs. So in such situations, what we end up doing is to split up the data and distribute the graphs among different machines, and then operate on those different smaller graphs individually, and then combine the results to produce the final result. Now, it so happens that if you have this distribution, then different nodes inside your system have to communicate with each other. And for some kinds of graph algorithms, this communication intensity is very high. And for some kinds of graph algorithms, this communication intensity is very low. Now, in the case of distributed systems, where the communication intensity or communication efficiency is reasonably low compared to a shared memory system, it is possible to have graph algorithms implemented very inefficiently, especially when the communication intensity is extremely high in the algorithm. So in such situations, what we need is specialized hardware. Now, in terms of the solution space, I mentioned three things. So one is the shared memory systems, where the graphs can fit inside a single machine, and we can operate on those, and typically we call them as the scale-up. Now, in the scale-out, we have distributed systems where the graphs are split up into multiple parts, and each of the nodes inside your distributed system is going to operate on a subgraph and then combine the results. And in the case of special purpose machines, we design custom hardware with custom interconnects so that we can put as much compute as needed and as much memory as needed. And these platforms are very efficient from both the compute and memory point of view. Now, Intel is working on advancing the technology in all of these three different areas. So in the case of scale-up, we have a memory technology called persistent memory modules. And this will allow us to put together systems which have up to 24 terabytes of main memory on a single server. So these kinds of servers can fit really large graphs, and they can solve most of the graph algorithms very efficiently. Now, in the case of scale-out systems, Intel is working on very efficient interconnects so that we can put together many different clusters with many different nodes inside them. And that way we can scale out the machines by as many number of nodes and as much amount of memory as is needed for the problem at hand. And of course, in the special purpose case, we are trying to work with the Department of Defense to design special purpose platforms so that they can handle very large graphs. Now, here are some numbers with respect to how Intel is producing a good performance for scale out and scale up. So the average performance is shown here, and the bar in the middle is the one where the performance of different algorithms is shown on a cluster of a Skylake machine with 32 nodes in it. And this is the baseline that we use. Now, the Cascade Lake server is a single node with about 6 terabytes of Optane memory inside it, is about 1.8x better than the 32 node cluster on the standard graph algorithms. Now, the latest recently released Ice Lake server, which has 40 cores in it, and it can get up to 8 terabytes of memory in it, is about 3.6x better than the Skylake cluster that we have. So that is how we are pushing up the scale-up solution. And then in the case of scale-out, if we take the 64-node cluster, then we get about 1.4x speed up. And then if we take more hardware and then throw 28 nodes in this cluster, then we get about 2.7x speed up here. So we are pushing both on the scale up.
So Ramesh, is the scale out using a special purpose interconnect, or is this just a normal Ethernet solution, or?
Yeah, I mean, it again depends upon the kind of machine that you have. In some cases, yes, we do use special interconnects, and in some cases, we do use the normal Ethernet. And usually, it is the library that is used for communication which takes care of all of that for you.
So the benchmark results you have here are based on Ethernet or some other interconnect?
No, this is the special interconnect that the Stampede cluster at Texas Computing Center has.
All right, thanks.
So this is an InfiniBand interconnect. Okay, so that is about the scale up and scale out. Now here is the special platform that Intel is building today. This is in collaboration with DARPA, which is the US Defense Research Agency, where they realized that graphs are very important, and they started a special program called Hive to fund the development of special purpose platforms. Now, as part of this program, Intel is building a special accelerator called Puma, which has very large memory capacity and dense compute. The ISA is not x86, but it is a special purpose RISC instruction set with the special graph instructions, which can accelerate the graph algorithms. It has a global address space that is accessible across all the cores and all the nodes in the system. Now, this system supports millions of threads, which has very low cost of switching between the threads. And also the network interface that is shown here is optimized to send very, very small packets with small data. And therefore, it is very suitable for accelerating the graph algorithms. Now, the paper that is listed here has a lot of details about the architecture and also some performance numbers in terms of the simulations that we have run. And to just summarize, we are seeing as high as 200x in terms of the speedups that we observe compared to traditional platforms on this machine. Now, the hardware is all great, but what about the software? So in order to ease the portability of software and applications across the shared memory systems, distributed systems, and also the distributed clusters and accelerators, Intel is developing something called OneAPI Framework with a new language called Data Parallel C++ and a set of libraries that are targeted at different domains. Now, the goal here is to provide a unified software development environment that can be used to develop software to run across all the current and future platforms that Intel is putting out. Now, the libraries provided in this OneAPI suite include the OneDNN, which is suitable for machine learning and AI. And it is there is a library called VPL, which is targeted at developers of media applications, and OneMKL, which is targeted at HPC developers. Now, Intel also partners with ecosystem to provide domain-specific libraries that can plug into the OneAPI tool suite. So for graph analytics, we partnered with a company called Katana Graph, which had its origins in the Galois graph frameworks from UT Austin. Now, this is the same framework that we used in some of the experimental results that I showed in the slide number 6 before. Now, Katana Graph is a company with deep expertise in
Ramesh, is the Puma architecture commercially available?
No, it's not yet commercially available, but we can have NDA relationship with some of the customers, and they can get a lot more details about it, and also use some of the pre-hardware enabling technologies that will allow them to run their experiments on that.
Okay.
If you have an interest, you can send us a request. It will be at a case-by-case basis with NDA. Yeah.
Okay, so Katana Graph is a company with deep expertise in graph analytics, graph ML and AI, and graph databases. So Intel is working with them to ensure that they provide a highly tuned and performant library for graph analytics and machine learning on Intel hardware platforms with a very rich set of algorithms that are shown here. Now, this framework will work with OneAPI tools and the libraries and will support both C++ and Python developers. Now, our expectation is that the customers of both Intel and Katana will be able to develop the next generation graph analytic applications using this library on Intel hardware. So now I will turn over to Roshan, who will give more details about the Katana framework, and especially how Katana Graph is accelerating machine learning and on graphs, which will allow us to get deeper insights than what is really possible with the traditional graph algorithms. So far, I showed only the traditional graph algorithms and where they're being applied, but the graph ML and AI will give you much deeper insights. So Roshan, take it away.
Thanks, Ramesh. I'm Roshan. I'm a co-founder and one of the architects of Katana Graph. And today I'll present how, in collaboration with Intel, we are building a software stack for graph analytics and graph AI. So first, let me say what is novel, or what does Katana Graph bring to the technology space. So Katana Graph is architected to handle massive data sets. So we have tested the very large data sets with a lot of customers, and we have also tested with the largest publicly available data set, which is a web crawl with 128 billion edges. Katana Graph is also engineered for unmatched performance compared to existing or competing solutions, where an order of magnitude are more faster than existing solutions. We have also engineered our system to provide both scale-up solutions as well as scale-out solutions. So we have shown that we can scale out as the results that Ramesh presented on supercomputers like Stampede, that we can scale up to 256 machines. We have also demonstrated that we can scale out similarly on HPC clusters. As we had a question on the interconnect and so on, we can also scale out on traditional HPC-based clusters from AWS, Azure, or Google Cloud. The other advantage with Katana is that we support a diversity of applications in many different domains, in health and life sciences, financial systems, identity management, high-performance computing. There are all these different domains, and there are different kinds of applications in these domains. It could be graph database related, graph mining, graph analytics, graph AI related. We support all of them, and we support all of them in the scale out the high performance mode. We believe the next challenge is AI. Graph AI is the next frontier, and we believe there is a lot of interplay between graph analytics and machine learning. So in graph analytics, typically you're computing graph metrics or graph labels, node labels or edge labels. You could be computing things like triangle counting or page rank in Google. And then you can use these metrics in your machine learning models to predict certain things about the graph. You can try to classify nodes, or you can try to predict links in the nodes, or use it in recommendation systems. And once you've built such models and score and classify data in these graph data sets, then you can use this to further explore the graph and compute new metrics using these ML results. So we think there is a close interplay between graph analytics and machine learning. So traditionally, there are a lot of machine learning and deep learning tools like k-means filtering, NLP, and classification. We believe that graph analytics, graph mining, and graph neural networks also fit closely into this space. So there are many kinds of graph AI techniques. It could be recommendation systems, graph embeddings, graph neural networks, graph transformation networks. All of this, I think, will together help address the next challenges in AI. In this talk specifically, I'll talk about two use cases: graph neural networks and graph transformation networks. Graph neural networks is an adaptation of traditional neural networks, traditional deep neural networks. In traditional convolutional neural networks, you're doing convolutions on images. In graph neural networks, there is an equivalent convolution on a graph. So you can think about a graph as, you can think about the image as a graph where the adjacent cells are connected. Then the convolution is simply a convolution on the adjacent neighbors in the graph. So graph convolution is defined in these spaces. And in graph neural networks, in addition to graph convolution, you have traditional neural network functions like activation functions, regularizations, and so on. The advantage of building these graph neural networks is that you can analyze and predict information about graph data sets. So for example, you could do node classification or predict the type of a given node. You could also predict links. So in recommendation systems, you predict whether two nodes can be connected or not, right? It's very similar. For a graph data set, you can do link prediction. And this can be used to say whether a link should have existed or whether you should recommend a movie to a user. Right? And similarly, you can also do prediction at the level of the graph itself. You could predict whether two networks or two subgraphs are similar to each other. And all of these have applications in a variety of fields, health sciences and intrusion detection and so on. So to do these predictions, graph neural networks compute what are known as node embeddings. So they compute some information about nodes. You could also compute information about edges. So you could have node embeddings, edge embeddings, or subgraph embeddings. And they can then be used in downstream tasks like node classification, link prediction, and network similarity. So what Katana and Intel bring to this is performance, right? So Katana AI on a Stampede cluster. This is the same cluster which Ramesh presented. It has Skylake machines. So we provide a native scale-out solution for running graph neural networks. So our solution is fast, it is distributed, it is parallel, and it significantly reduces the training time compared to existing solutions. Moreover, there's no accuracy loss. So here are two data sets. So these are all real-world data sets. One is a data set consisting of Reddit posts, where both the posts are nodes. And the relationships are, they connect posts if some user has comments in the same post. So what we want to classify nodes is in communities. So there are these subreddit communities. Right? So we automatically want to detect these communities. And that's what this graph neural network does on Reddit. Similarly, there's a product database where we have Amazon products and connecting products. There's an edge between two products if they're purchased together. And we want to classify them into categories. Are these books? Are these electronics? Are these something else? Right? And here is the performance that we get. This is a specific graph neural network known as graph stage. I'm showing you for two different inputs here. The x-axis represents the number of machines that we are running it on. And the y-axis is the training time per epoch. Right. So you run typically 200 epochs or similar things for these data sets to converge to a good accuracy. So as you can see, the existing solution, which is shown in orange here, is much slower than us and they don't scale up. But if you look at Katana, we are not only faster than them on a scale up mode on a single machine, but we scale out much better than them.
Roshan, is this, is that benchmarking data, is that with GPUs or CPUs only, or?
So this is just Skylake machines. This is just Intel CPUs.
So no GPUs at all?
No GPUs at all in this one, yes.
Okay, thanks.
Yeah. Katana does support accelerators as well, but these results are on Intel CPUs. So there are more advanced data sets. For example, if you look in the medical community, they have what are known as knowledge graphs, right? And these are graphs where there are types and properties on the nodes and edges. So this is the schema for the graph. You could have nodes like molecule dictionaries, activities, drug indications, compound records, and so on. And there are millions of nodes for each of these type of nodes. So using such data sets, you can run certain traditional queries in the graph database that Katana has. You can run things like, what drugs can I prescribe for malaria that are not known to have adverse side effects on kidney functions? In addition, you can run graph AI techniques on this. So specifically for these heterogeneous or property graphs, there are more advanced graph AI techniques like graph transformer networks. Here, they define what are known as meta paths, which are typed paths in a property graph. Assume you have red, blue, and green types, edge types in a graph, then you're trying to find a path which has red, blue, and then green. So that's a specific path that you're trying to find. What these graph transformation networks do is they learn these useful or important meta paths in a property graph automatically. And then they use this to learn node embeddings. So they internally use graph convolutional networks after they learn this meta path. So it's a part of the training process itself. And Katana Graph, in collaboration with Intel, is providing a native scale-up solution for these GTNs. So we have a very fast parallel GNN architecture implementation, which significantly reduces the training time. And again, there's no accuracy loss compared to existing solutions. Here I'm showing you two different data sets where there are different types of nodes. So for example, in the DBLP data set, there are papers, authors, and conferences. There can be different kinds of relationships. You can have relationships between paper and authors. You can have relationships between paper and conference. And what you're trying to classify is you're trying to classify the nodes into research areas. Which research area was this paper published? Similarly, you could do something similar for movies, actors, and directors and try to classify them into genres. So here I'm showing you results for three different data sets. ACM is another DBLP-like data set, but it's slightly smaller. The blue graph is, the blue bar is PyTorch, which is the existing solution. So if you notice, we are 2 orders of magnitude faster than PyTorch. This is due to various innovations in our system, both algorithmic as well as software implementation related advancements. And if you compare the accuracy here, this means that there's 75% accuracy. So accuracy is comparable or is it better than existing solutions. Thus, Katana, along with Intel, is able to provide both scale-up and scale-out solutions for Graph AI. We hope we have convinced you that Katana, in collaboration with Intel, is working well within the Intel OneAPI ecosystem and is providing novel and effective Graph AI solutions. And there is an ubiquity of the Katana framework solutions on Intel platforms. We provide solutions for both public clouds and on-prem clusters as well. We provide solutions for scale-out and distribute systems, or on accelerators. We provide scale-up solutions on shared memory systems and accelerators as well. And our system can be coded using C++, Python, graph querying languages. They can use our system. And as I've shown, we support a diversity of graph AI and ML models.
So the graph neural net kinds of solutions, do they plug into something like TensorFlow Keras or something like that, so that you could take a model that's CNN, for instance, and convert it to a GNN model, or how does that work?
So there's a lot of work on the API part of graph neural networks as well. So there are other competing solutions, and we are also working with other collaborators. But yes, so you could work with TensorFlow, PyTorch, such kinds of systems, and try to modify just the graph-related components. These graph convolutions also provide graph-specific operations. So TensorFlow as is might not be sufficient. So we need to identify that there's a graph data structure involved, or there's a sparse matrix structure involved.
And aren't all neural networks effectively graph structures?
So neural networks are dense tensors, right? So neural networks are on dense tensors. Here, what we're talking about is a specific sparse tensor. It's a two-dimensional sparse tensor, a sparse matrix, right? So it's useful to look at it in that way because you can perform more operations on it. For example, the graph transformation networks that I presented, our key innovation is that in the PyTorch implementation is looking at it in terms of matrices and implementing it in terms of matrices. Our key innovation is that we look at it in terms of graphs, and we're able to do other kinds of operations, analytics kind of operations, like doing random walks and so on, to sample the graph and give better solutions in the end.
So what sort of types of operations do GNN typically work well in? I mean, CNNs are image classification, image detection, that sort of stuff. GNNs would work well in what sort of applications?
So there's a lot of demand for GNN. At least I can talk from what we have observed. So there's a lot of demand for GNNs in the biopharma and biomedical community to detect whether two chemical structures are similar, to detect whether something is a potential drug for a disease, and so on.
I could see a very, very interesting application in the intelligence community with, terrorist networks and things of that nature, trying to map what's going on in that respect.
That's exactly what I was going to say, Ray.
Josh is the guy.
Yeah, this would be a great tool for mapping social media networks and bots and artificial amplification of disinformation. I like the possibilities there.
Yeah.
There are two key things. So link prediction is one, as Roshan was saying, and then node classification is another one that machine learning is used for detecting what is going on inside your data that is not evident from the existing set of data. And those are very powerful techniques that traditional graph analytics are not able to handle, but machine learning and AI are able to handle that and give you some very deep insights and predict what might happen in future.
What's the onboarding path in terms of engaging with Katana on this? Because the site suggests that, is it kicking off a project? Is it just buying the kit? What is the kind of happy path for somebody who has this big graph analytics challenge right now?
Yeah, thanks for the question. So the path right now is to contact us and engage with us. So we are also, we are a startup. We are coming up with a public release soon, which can be deployed on public clouds and so on. We also have an open source. We are quite. Not all of our code is open source. We do have enterprise code, but we also have an open source repo, which we make available for people to try out to try out their solution and try it out. So you can definitely try out our open source solution. You can also contact with us to get early access to our enterprise repo. And we do have close collaboration with all our customers right now.
Yeah, but what we're trying to do is to provide a capability with Katana library similar to what you can get with NetworkX in Python today. So if you're a user of NetworkX, then you should be able to replace that with Katana Graph and get an order of magnitude performance boost on Intel hardware.
Yeah.
Specifically on that note, all our code related to the Intel OneAPI system will be open source. So the Python interface, right, being able to interact with NetworkX, all of that is open source, and people can directly use it.
Yeah, and if this is Arijit, any company is interested to do any kind of a POC, the Katana Graph is in the Intel's disruptor program, so there will be a set of goodies and stuff that can be provided. You can reach out to the Katana, the Intel team, to Danielle as well, and we can kind of roll that into the POC models.